Okay, guys, today we're going to be talking about section 7.5 of your textbook, and we're going to be solving just a little too close to the top here. Solving exponential and logarithmic equations. You may want to take some notes during the video, but the video will remain on Canvas. The video will remain on Canvas if you want to refer back to it. Okay, we're going to quickly hit a topic that we did a little bit of on Wednesday, and that's the idea of giving both sides of the equation common bases. If you have the ability to give both sides of the equation common bases, it's usually the quickest way to solve your equation. For example, 3 to the x plus 2 equals 27 to the 2x. Okay? What I can do here is write both sides as a power of 3. Obviously, the left side is already written as a power of 3. So 27 I'm going to replace with 3 to the third. And we know from our rules of exponents that when we take an exponent to another exponent, we multiply those. So what I have is 3 to the x plus 2 equals 3 to the 6x. Once my bases are equal, in order for these equations to be equal, the exponents must equal each other. So I say x plus 2 equals 6x. 5x equals 2. X equals 2/5. Now, we're going to be talking a little bit later about extraneous solutions. When it comes to exponentials, we don't really have to worry about extraneous solutions since the domain of exponentials is all real numbers. Okay, I can put anything I want in for x on either side of this equation, and that equation is going to be defined. If you would like to check your solution, you can certainly use a calculator, plug it back in, and check your solution. Okay. Now, what happens if we can't give things common bases? That's where the development of logarithms comes in. For example, 15 to the 3x equals 285. Okay, obviously I can't write 285 as a power of 15. Neither can I write 15 and 285 as the power of any common base. So this is where our logarithms come in. The best way to approach this problem is using the change of base formula. Let's review the change of base formula. In the change of base formula, the exponent is equal to the log of the argument divided by the log of the base. Now remember, when we use log, we're using log base 10. And the reason we choose log base 10 is that's what our calculators do. So you can use any base you want, but for our purposes, log base 10 works the best. So remember now, this is just in a different form than when it's in the logarithmic form, but our argument and our base don't change. So our exponent is 3x. That's going to be equal to the log of 285. That's the argument, over the log of 15. Now, a lot of people want to cancel the 285 and the 15, but please don't do that. Once they're the argument of the logarithm, that number is not 285. It's the log of 285, which is a completely different number. So I'm going to go ahead and go to my calculator. And let's go ahead and clear this because I have stuff on here. And I'm going to do log And then I'm going to do 285. Let's get too many parentheses there. Let's go back. Log 285, remember to close that parenthesis, divided by log 15. And close that parenthesis and hit enter. So that number is approximately, let's go 3 decimal places, 2.087. So what I have now is 3x equals 2.087. And then to solve for x, I'm obviously going to have to divide that by 3. I'm just going to go right back to my calculator. Instead of typing that in again, I'm just going to hit divided by 3. And my answer is 0.696. So x equals 0.696. Okay, and again, we don't have to worry about checking it as far as extraneous solutions go. But if you want to go ahead and go back to your calculator and plug it in, if you plug in 6.96 in for x, it's not going to be exactly 285, but because you rounded it. But let me show you on your calculator how you can do it without actually rounding. We have 15 to the power of 3x. So if I go back to my calculator, I can do 15 to the power of 3 times, and then instead of typing in 0.696, I can just hit second and the negative sign. Let's try that again, second and the negative sign. And that says take 3 times my previous answer, and you can see I get 285. Okay, so it is appropriate to go ahead and check your answers on the calculator. But you're not only checking them for accuracy, you don't need to worry about checking them for extraneous solutions. Okay, one more quick example here before we move on to using the calculator and graphing to solve exponentials. 5 minus 3x equals negative 40. Okay? Before I can use the change of base formula, this exponential here has to stand alone. So just make sure that you subtract 5 from both sides. So you get negative 45. And then go ahead. Now remember, there's no parentheses around here. This is not negative 3 to the x. It's 3 to the x and then take the negative. So I'm going to go ahead and divide both sides by negative 1. So I get 3 to the x equals 45. Now I can go ahead and apply my change of base formula. My exponent equals log of the argument divided by log of the base. And again, do not cancel the 45 and the 3. Okay, so go back to my calculator. Log 45 divided by log 3. And I get 3.465. 3 point, let's go back there for a minute. Okay. 3.465. And again, if you want to check that answer, you can go ahead and plug your answer back in and see what you come up with. All right. Okay, let's talk about how to use a calculator. How to use, we're going to first use the graphing feature of our calculator. So use graphing feature to solve. So if I wanted to solve this exponential, 4 to the 3x equals, and we're going to use a big number just so we can get some practice on changing our windows in our calculator. 4 to the 3x equals 6,000. I am going to graph two equations here. I'm going to graph y equals 4 to the 3x, and then I'm going to graph the horizontal line y equals 6,000. And when I do that, I'm going to find where the two graphs intersect. Okay, the point where the two graphs intersect is going to be the point where 4 to the 3x equals 6,000. So let's go to our graphing calculator. Let's go to y equals, and I'm going to put 4 to the power of 3x. Okay, and then hit enter. And under y2, I'm going to put 6,000. Now, if I graph this right now, I'm looking for where y is 6,000. My standard viewing window only goes -10 to 10 on the x and -10 to 10 on the y. So I need to change my viewing window to make it appropriate. So I'm going to now go to second. Well, I'm not even going to hit second. Sorry, I'm just going to hit window. And your x values are okay. The one that's really going to give you the issue is the y value. Okay, so I need to come down here and change my y maximum. Yeah, y maximum. I'm going to come down here and change my y maximum. Now, I don't want to go to 6,000 because I need to see a little bit above that. So I'm going to make it go 7,000. Okay, and then I'm going to hit graph. So you're going to see your exponential of y equals 4 to the 3x. And then you should see your horizontal line, y equals 6,000. What we're looking for is the x value where those two lines cross. So you're going to hit second trace to pick up the calc. And I'm going to go down to intersect and hit enter. And it's going to ask you a couple of questions. It should ask you for first curve and second curve. Let's go back again. Second calc. Intersect. Enter. Okay. It asks me if I'm on my first curve. Let's go. I'm going to move my asterisk to the right a little bit so you guys can see it. Okay, I'm clearly on one curve, so I hit enter. And then it says, is my asterisk clearly on the other curve? And I'm going to hit enter. Enter past the guess. And you can see that the y value is 6,000, obviously, because we're on the line y equals 6,000. The x value is 2.092. So if I go back here, that tells me that x is 2.092. Again, if you want to go back to your graphing calculator and check your solutions and do 4 to the power of 3 times 2.092, you should get very close to 6,000, although it won't be completely accurate. Okay, now we're going to look at using the table feature. Using the table feature of our calculator, we can do that also. So back to the calculator. I'm going to hit, now remember, I'm looking for where the point that both graphs have in common. So I'm going to go to my table Hit my table button. If it'll go. Oh, I'm sorry, I'm on trace. Okay, notice the y values in blue are the y values on the exponential curve, y equals 4 to the 3x. And obviously all the y values on the red curve are 6,000 because it's the graph y equals 6,000. So as you can see from the table, I want to know where y1 is also 6,000. So it's somewhere between 2 and 3. So what I can do is I can change my table settings. We already know the answer is 2.096. But I know that it's somewhere between 2 and 3. So I'm going to go to this table set button. Try that one more time. And I am going to have my table now start at 2. Because I know that my answer is somewhere between 2 and 3. And then this is the change in x I want on my table. So right now it's set to go, my table's set to go from an x value of 2 to an x value of 3 because it's set to change by 1. I'm going to have my table change by 0.01. Okay, now I'm going to go back to my table. Now, as you can see, my x values are now changing a little bit. So I'm a little bit closer to seeing now that somewhere between 2.09 and 2.10, my y1 is going to be 6,000. So if you want an even more accurate answer, you go back to your table set and make your x change by 0.001. And then go back to your table. And now you can see my x values are really changing there. So you're going to have to scroll way down to get to it. And I'm still scrolling. So usually most people like the graphing method better, but your textbook asks you to do it both ways just so you get the feel of both methods. I'm probably going to pass it now because I was holding down my button. We're going to pass it now. Remember, oh, there we go. So I'm going to hit the page down button. Oh, page down doesn't do anything different. Getting there. What was our answer? 2.096. I probably should have started my table with something other than 2. There we go, we're there. Okay, so now you can kind of see, uh-oh, I did pass it. I did, I hit the button too many times and I passed it. Okay, but you get the feel of that. All right, this now brings us to our last topic of solving logarithmic equations. Okay, and again, you have a little bit of experience in this. Okay. We know that we solve logarithms using exponentials. We turn our logarithmic equation into an exponential. But before we do that, that log has to stand all by itself. So the first thing I'm going to do is divide both sides by 2. Some of you may be asking, could I have put that 2 back up in the exponent? And the answer is yes. Okay, now we know that there's no base written here, but we also know that if there's no base, it's a base 10. So what I'm going to now do is turn this to an exponential. So 10 to the negative 1/2 equals x. I'm going to switch mine around just because I like it the other way. That's 1 over 10 to the positive 1/2. And we know that the 1/2 power, we know that the 1/2 power is the square root, so this is 1 over square root of 10. We also know we can't leave square root of 10 in the denominator, so we're going to go ahead and rationalize that. So x is root 10 over 10. Now, when it comes to solving logarithmic equations, if you remember correctly what the domain of our logarithmic equation is. The domain of the logarithm is 0 to infinity. What that is telling me is this argument here must always be a positive number. So if I went and plugged root 10 over 10 in there, that's a safe answer. Root 10 over 10 falls in the domain. Okay, now we're going to talk about when it shifts. That's a little bit different story. But root 10 over 10 does not make that argument negative, so I do not have an extraneous solution. Okay, let's try another one. Log, ooh, that color's not good. Log of 6x minus 3 equals negative 4. Okay, I'm going to go ahead and add the 3 to the other side so that my logarithm is standing by itself. Again, there's a base 10 there. We're going to change it to an exponential. So 10 to the negative 1 equals 6x. So 6x equals 10 to the negative 1 is 1/10. Dividing both sides by 6, I get 1 over 60. Okay? Once again, on these logarithms, you could come up with extraneous solutions because we have a restricted domain. But if I plug that answer in there, does it make the argument negative? And the answer is no. So my answer, again, is a fine answer. It's not extraneous. Okay. Another one. Log of x minus log of 3 equals negative 4. Okay, if we want to do this problem now, before we can change it to an exponential, this left side of the equation has to be a single logarithm. So we use our properties of logarithms. Because my logarithms are subtracted, I can combine them into a single logarithm where the arguments are divided. Once I have a single logarithm, again, we know the base is 10. So once I have a single logarithm, I can now change it to an exponential. 10 to the negative fourth equals x over 3. That tells me that x over 3 equals 1 over 10,000. Multiply both sides by 3. X is 3 over 10,000. Okay, remember to go back to your original equation. Does that make that argument negative or 0? And the answer is no. So again, we have a safe solution. Okay. One more. We'll get maybe a little bit more complicated with some of our properties of logarithms. Log of 2x plus 1 equals log of x plus 2 minus 1. Okay, there are several ways you could solve this problem because there's a couple of properties of logarithms that you can go ahead and apply. One of the ways we looked at today is to replace 1. Now remember, our base is 10 here because it's not there. To replace 1 with log base 10 of 10. Now I have 2 arguments over here. 2 arguments over here that are subtracted. I'm going to condense them to one logarithm. I'm sorry, we have 2 logarithms over here that are subtracted. I'm going to condense them to one logarithm where the arguments are divided. Okay, now this is sort of a cool feature of doing it this way. Just like when we had common bases, when we have a single logarithm on either side, so I have a single logarithm here with common bases, if these 2 sides of the equation were to equal, the arguments have to equal each other. So 2x plus 1 has to equal x plus 2 over 10. And we have a simple algebraic equation to solve. I'm going to multiply both sides by 10. I'm going to distribute the 10. And do a little work here. Subtract the x over. I get 19x equals negative 8. X equals negative 8 over 19. Okay, let's go back to our original equation. Very, very, very original equation. Right here. Oh. Will my value that I got of negative 8 over 19 be okay? Will it make either one of these arguments, either that argument or that argument, negative? And the answer is no. It doesn't make either one negative, and you can kind of use a calculator to plug that in and make sure that your arguments are negative, or not negative, or 0. But my point being here is just because your answer is negative does not automatically make it an extraneous solution, okay? That answer has to make your arguments negative for it to be an extraneous solution. So my answer is fine there. Okay, so that is our lesson for today. What you are going to work on now in class is enrichment number 5, which is the 7.5 practice worksheet. Okay, I believe I put on there to do odds only. Your sub should have the answer key so you can check your answers as you go. You also have an EOL for tonight. So good luck, and I will see you guys on Wednesday.